Okay, so welcome back to another stacklang session, and in this part what I want to do is to finish up the if statements. So let's add some labels so we can have multiple if statements in a function. And yeah, I just improved a bit the readme with some specs about the language, and yeah, it's still work in progress because we have a lot of stuff to add on top of this, right? Like right now I just described what we have and what I plan mainly to do maybe today or in the near future, like next few days. So yeah, right now a stack program is just a list of data types and functions. Maybe we'll add something else, I'm not sure yet. It's not gonna be like OOP stuff because I don't really like OOP. I still think that structures and functions is the best way to code. Like Go does a really good job at doing that. So yeah, that's pretty cool. Even Rust does the same thing. So maybe we can try to learn from that and try to do something similar with interfaces or traits, something like that. Yeah, so currently we only have integers and booleans in our language. We'll try to add strings because we want to print hello world in stack, so that's gonna be useful. Maybe first time is gonna be printing hello world by using integers, so character by character, so we can even see the improvement of then using a string and making the program like one line. So that's also something we can do. Then we have functions, right? So we had some data types, functions. We also have custom data types, but first let's see the functions. So functions are pretty basic. You just write the func keyword, then the function name, then we have the list of inputs and the list of outputs of the stack. We don't really use these ones yet, but we'll use them in type checking, and I'm pretty curious how type checking is gonna work. So that's gonna be, let's not say it's gonna be fun because it's probably is gonna be painful, but it's gonna be interesting nonetheless. So yeah, stay tuned for this part because it's gonna be really interesting to see how we can do type checking and type inference in this language, right? Then we have in keyword, then the body of the function, which can be like expressions, so other functions. You just call them by writing the name of them. You can also put numbers, booleans, strings when they are going to be available, but you just list them here and it's going to do them step by step basically. And the end keyword to know when the function is ended. And yeah, why I said type checking is going to be interesting is we also have this kind of functions which are embedded in the compiler, let's say, but they are generic, so they can take any kind here and they return the same thing twice. For example, dup, which duplicates the first item on the stack, right? And the thing is that this a is kind of dependent on the context. So if you use dup after an integer, then a is an integer, right? It makes sense. But if you use dup after a string, the a should become a string. So that's where I think we need some kind of inference. And obviously the inference is going to be at compile time. We won't have any dynamics. I hope it's going to not turn into a dynamic language. Like currently we don't have any type checking. So you have to make sure that you know what you are doing, right? But once we add type checking, pretty curious how it's gonna work, especially with this generic stuff, right? And another example of generic is swap. And what's interesting to think about swap is you can have actually, so swap will swap around two items from the stack, right? But they don't have to be the same type, so they are gonna be A and B types, and then return result will be B and A. Right, so you can swap an int with a bool, so swap them around, or an int with a string. Right, and then we have rotate, which just takes the first item and pushes it back 2 slots. So again, it can be 3 different types here. And if you have int, then all of these should resolve to integers. So yeah, A, B, and C. So we'll see how we are gonna do all of these mappings. Like it's gonna be like a graph or some structure like that, right? Anyway, we also have a pop function. This is really useful when you implement recursive functions with if statements, because you kind of want each branch to return the same thing usually, because that's gonna make things much easier, right? If you have an if statement and one branch returns 5 integers and one branch doesn't return anything, then you know, at some point when the type checking is going to be implemented, at some point you need to resolve that thing, because type checking won't be happy if, you know, all the paths of a function don't return the same thing, right, at the execution. So yeah, pop function will be useful for if statements or for while loops, if we are going to have while loops. I'm not sure yet, but yeah, I mean, they are pretty similar to if, so probably it makes sense, right, to avoid the recursive approach. Like if you want to implement it recursively, you do it with recursion. If you want to use while loops, you use while loops, so why not? Then we have some math functions. I still have to add subtract and division. You know, didn't really need them, so skip them. Then we have greater than, and what's really annoying about functions is that you have to get used to using them. So, and the reason is the arguments are gonna be reversed when you look at them in the code, but on the stack they are in the right order, right? So, for example, if you do 0, 1 greater than, it's gonna return true, and the reason is when we take the arguments for the function, we first pop a 1, so 1 is the first argument, it comes here, and then 0 is the second argument and it comes here. So 1 is greater than 0, right? So yeah, you have to get used to using these kinds of function. Honestly, I'm still struggling, especially for like most of these, like plus, multiplication, don't really matter about the order of arguments, but minus, division, greater than, less than, they kind of matter, right? So you have to remember that yeah, arguments are in the reverse order. Even type checking is going to be important for that, right? So yeah, also have equals, and that's kind of it. Maybe the out function is gonna print an integer to the std out, and what I was thinking, maybe we are gonna do that pretty soon, is that right now, since we had only one data type, only integer, I made all the functions that are for integers, just plus, multiplication, and so on. But if we are gonna add more data types, maybe it's fair to add a prefix to the int functions, like this: int and then plus, int star, int greater than, and so on. And you know, that way we are gonna have float plus. But there's also the option to keep integer as the, you know, king of the data types, and it doesn't need a prefix for its operations. So int is gonna be like a special case with no prefix, and all the other data types are, you know, recommended to have a prefix in front of them. So we can also do that, but it is what it is. Yeah, anyway, let's go to expressions now, right? We can have literals, so just integers, booleans, and maybe strings. We'll try to do them today. We also have function calls, which you just put the name of the function in the body of another function and you just call it. You know, this kind of goes to, maybe we can have recursion. That's interesting. And we also have conditionals, right? And conditionals are if statements. So an if statement, you can think of it as a function that takes in a boolean and produces some stuff on the stack, and the stuff it produces, it depends on what you have on the if case and on the else case, right? So you can put anything in here. And the other thing about if statements is that the else case obviously can be missing. Think of it as if it's empty, you can just omit it, right? And even this thing can be empty and then you just use the else, right? So maybe an example would be a function that returns the absolute value, and it's a function that takes in an int, returns an int, right? So if the number is less than 0, we multiply it with -1, and on the else case we don't do anything, so we can just omit it. If you want, you can just write it and don't do anything, or you can even implement it I guess like this, and then do it like this, and then the if case is empty. But it feels like this is the least amount of characters you write, so why not just go with the minimum? Yeah. And then I have an example that we can try to test today after we implement the out function. I'm not sure if it's gonna work, but it should print all the numbers in order from 0 to n. But yeah, I haven't tested it yet because I don't have out. So it's implemented using recursion, right? We have this show n prime function, takes in two numbers. One is gonna be the iterator that we print, and one is gonna be the limit. So we do some rotation, dupes, and so on. And on the if case, we print the number, and then we recursively call to the same function, right? And you can see that here I put all the stuff that's on the stack, right? Just to keep track of what's happening. But ideally you would use the type checker for this. It still makes sense to write comments with this stuff while you implement it. Maybe after you are done, you just remove them. I don't know. But yeah, here we call recursively, and on the else case, as I said, we want to make sure that the type is the same. Right now it doesn't really matter, but it's kind of useful to know that both cases return empty, so you don't have to deal with weird type checking errors, right? And then obviously custom data types is the final thing that we have right now. And I guess you saw this, you define it with data, the name, and then the fields. And the idea is that the compiler will implement the constructor and field getters for you. So constructor is going to be a name of the structure, and that's how you build the data structure. And again, you have to make sure that the field, these integers are in the reverse order compared to the definition, because that's how the stack works. And then the getters are just functions that give you each field, and the name of the getter is going to be structure dot field name, right? And yeah, here I have an example for dot product, which we saw before. And obviously the entry point is going to be the main function, and I guess right now main function should always return an integer, which is the status code. And the reason for this is because I don't have a really good way of actually printing stuff, so I just use the status code as the printing, right? But we'll try today to add the out function. So I have a to do for out and a to do for strings. Perfect. So yeah, let's start with the implementation. And actually the first thing that I have to do is yeah, the code that I don't like. Yeah, so if statements right now they work, but you won't be able to use more than one if statement per function. The reason why is that we have here this if label, but we need to add some kind of %d to it or something to make it let's just say, you know, each if statement has its own label basically. So yeah, we need some kind of I mean, it can be unsigned int if counter, let's say it's going to be 0 for now, and it's going to be a u, right? If counter. Then we just need to search for all the ifs. So for example, we have another if here, or I guess another, it's a phi, but if counter. Then we have the label here, we have another one here, so it's the if counter. And well, yeah, I don't know why it, I mean, fair enough, let's use rd. But right now the if counter, I guess it's always 0, right? We need some way of incrementing it. So for example, when we get into an expression, we don't really know what's gonna happen, right? Maybe we find another if, maybe we, I don't know, but yeah, here we actually found another if, right? So what do we want to do is to probably have this if counter on the assembler structure. So let's go here and have something like unsigned int if counter. So where is our, yeah, I mean, actually this function should probably be like here, and let's have the init function be the first one, so we can do stuff like assembler if counter is equal to 0, and we have also assembler 3. I would also move this one here just to have both of them close. So assembler if counter is equal to 0, just to make sure that all fields are set to 0. Okay, so now if we go back to our if statement, right, I guess here we could just say that we take the if counter from the assembler.if counter, right? And yeah, let's do that, assembler if counter, and we also increment it, right, because we found an if. And I wanted to also show the case where you use the if counter directly, but you know, that wouldn't really work, right, if you think about it, because here you go into another expression, so you change the assembler. And what if you actually change the if counter, right? When you use it here, it's gonna be different than the one you used here. So I guess that's gonna be, that is something that Rust would fix, right? Because it's gonna be here you need to borrow it like with mute, and then you borrow it without mute, so it's gonna say that you cannot do that, right? Am I right with that? Do I know Rust? I guess I do. So I think this is gonna work actually, and it's gonna generate the labels. I mean, obviously it's gonna be like number for each if. We don't really need that. We only need to number the ifs in the same function, but I mean, it is what it is. We don't really, it doesn't really matter in the end. So if we build this one, right, again, it's gonna say 0. And if we go into example asm, you'll see here it's if 0. Oh, the else case, I forgot about else. But else doesn't even matter, honestly, because else is not used. But it's, you know, a good idea to if counter it. Actually, I'm curious. I think if you define the same label twice, it's gonna error. So, yeah. And let's try to have two if statements. So here, let's do something like true if. So it's just gonna do this one always on the else case, right? And then let's do another if here, if, or I guess true if pop, or I guess we don't do anything and else we pop, or something like that. Just do not change the function. So if we build, right, and let's check out example.asm, we should see now multiple if statements, right? So here you can see that jump node 0 to if 0, and if 0 is down here, and the ending is also here, v0. And then on the else case, we actually jump to if 1, which is here. So it's nested into else, right? So yeah, it's nested. And here we have the other if, which, you know, doesn't really do anything. So yeah, I guess the if statement seems to work. Perfect. So yeah, I guess that's all for the if statement. I mean, yeah, let's add the out function next. So to add the out function, we want, so it's gonna be an integer function, right? So there isn't actually a good way of printing a number. So how can we actually do that, right? Because we need, I guess what I can do is to just, let's do the following. Let's go to readme. Let's take these functions. Let's show n and whatever. Let's go to example and let's just plop this thing here. Maybe I'm also gonna do at some point syntax for Vim. That's useful. And let's do show n, maybe 10, the first 10 numbers, right? So if I'm gonna compile this, it's not gonna work because we don't have function 14, which is the out function. So let's go into the assembly and let's try to actually implement it. So let's see, function, curious, the order is so weird, 6, 7, 8, 10, whatever. Let's do function 14. Out int, right? So function 14. So it makes sense to pop, obviously, into RAX, let's say. All right. So how can we, I mean, we could say that out int actually prints the integer as a character, but I want to print the int itself though. So I want to show the actual integer. I guess we did something like that in the call compiler at some point. I don't know if I still have it. So here we should have out int, but I converted it to string. And this is class IO. So here it's okay, let's see to string on the integer. Where is it? I think it should be an extern function, or is it not? No, it's no longer, yeah. So actually I changed it to this thing. Which, you know, made sense. But yeah, I still think would be useful to have it just for now, even if we are gonna implement it in the standard library like this, by adding the byte data type, for example. Which, yeah, so here also did this kind of stuff. Yeah, I mean, converting the integer to a string, right? That's a fair point. So maybe just to make things easier, we can just print the characters. Or something. I mean, we have toString for bytes, which could be useful. Yeah, I think, yeah, could be useful because we do toString here. So maybe it's gonna be useful to see how the byte toString is implemented. Okay, let's try to find that. So it should be byte toString. Damn. Oh, but I don't have a call to any interesting function. Yeah, I mean, I guess other option. So yeah, let's try to just syscall write. Okay, so syscall write, and then let's do like assembly or something. I just want to see the assembly for write. Why? So we can, man, it's okay. Let's go back to the cool compiler because I have implemented the write syscall, so we can just look at this thing. So the syscall for write, we put arguments in order: RDI, RSI, RDX, right? And RX is the syscall. So let's just copy this thing. let's just copy this thing. And if do we have, no, I'm not sure. Okay, let's see this, the manual page, right? So we put the file descriptor into RDI, we put the buffer into RSI, pointer to the string, for example, and in size t we put a count. So RDI is gonna be the std out, right? And std out should probably be std out number c. Huh, no one knows the number. I think it should be 1, right? And std in is 0. Okay, so we write to std out. Then in RSI, what if we put RAX, but we don't dereference it? Like, what if we put the address to RAX? Right, that's what I'm thinking. So the address to the number, right? And here, what if we say we want to print only one character, like 1 byte? All right, so in this case, let's go from FASM step. It's segmentation faulted. Okay, makes sense. I guess, I don't know. What if we don't do anything though? Does it still seg fault? Yeah. Huh. So maybe it's something wrong in example.sl though. But what could be wrong? And maybe what we want to do first is just test the outInt function itself. So in main, instead of calling show n, let's call out, which is, I remember it's 14. Yeah, it's 14. So let's try to call the out function. Still crashes, what? Okay, that's really strange. What if we do this thing though? Yeah, that doesn't make sense because we don't put yeah, obviously we don't put a return on the stack. So let's put a return on the stack, right? Let's put a 0 on the stack. All right, so it doesn't show anything here, right? So let's do back show n. Let's go back to show n, and still doesn't really show anything. Okay. I guess at the address of RAX, we have 8 bytes, right? So maybe we have to print 8 bytes to show something. Okay, that's weird. Yeah, I was just trying to... What if... Oh, but I still haven't installed GDB. Damn it. I forgot about that. Okay. Yeah, so here array X is gonna contain the address to the heap where our number is. Yeah, I mean, it can make sense if the maybe if we try to push a really big number, is there a way to make the entire register once, so it's like 1111 for everything? I'm just thinking, if you XOR it with something, if you OR it or AND it, if you negate it maybe, but I don't know. Assembly flip all bits in register. Yeah, but XOR with 111. You could use AND N. Oh. $1 FF, or what is that? Also, this is an actual number. So this would be all ones. Okay, I mean, probably the value is gonna be in AL, right? So move. Oh, but I'm wrong. It is array-x, but do I have to plus 7? No. But let's put a character that we think shows something. So it would be like 65, right? If we check in Python, it's A, 65, right? So it should show A though. If I do Rx plus 7 here. Oh. Oh, so we get an A. That's interesting. And show n. But, you know, I mean, let's try show n prime. Show n prime. And show n prime actually takes in both the numbers, the start and the end. So we can do something like, but I need to remember the order of them. So it's first is the n and then the I. Okay, so we could say first is the n. So let's push another integer. And let's say we want to print 10 characters, right? And if I call this one, what? Oh, I did 14 again. It should be 13. Wait, isn't it 13? Yeah, it is. 1 second, did I put them in the reverse order? Yeah, I think, actually I don't know. No, I did not. Oh, so n should be actually 75. It's not how many, it's from what to what actually, right? I put them. Wait, what? Okay, let's see again the example. So example is from I. So I is the first argument, n is the second one. So I is what we print. So if I is what we print, then we should push n and then we should push I on the stack. So first we push n and then we push I on the stack. Yeah. Right. So it should be like this. It should be like that. So 65 is gonna be I and 75 is gonna be n. Now maybe it's wrong in the implementation. So yeah, but okay, so we kind of know how out will work. It's a bit scuffed for now because it prints characters. Oh, you know what other language that I did? Is the BF compiler. In this one, actually, I have printing the number like a character. So generate assembly output. Oh shit, it's exactly what I did. It's 1 pointer 1. But thing is that here the pointer was a single character, right? So it worked, obviously. But here we have more than one character, so I don't know. I don't know why this one worked and this one didn't. And again, I think it might be some weird thing with my stuff. So let's see when we create an integer. How do we create it though? Maybe it's something there, int constructor. So we allocate 8 bytes, right? And then we move at this address the rex register. Man, I should really install GDB and just take a look at it. So yeah, let me try to just install GDB and take a look at how this thing runs, right? So see you in a bit. Right, so I have a GDB and now we can try to breakpoint into the start, right? And then run. And we should be able to see them. Hopefully it's visible. But we should be able to see all the registers and somehow the code, but the code is in assembly, right? And here is the stack. It's not our stack, but it's the stack, right? So here I think we do step instruction. So this should be allocating the memory, and yeah. So let's just go through this until we reach something that looks like our code. Oh, interesting, we have some jumps. Still not sure where. Let me just continue to stop it. Can I figure out address of main? Like I cannot breakpoint func 0. Yeah, but I can just breakpoint start, right? And start is like here, and it does allocator init. It's 3 syscalls, okay, and then it calls to main. Let's actually try to find it. So I guess first thing that's gonna happen is push rbp, move that thing, and then it puts 12, right? 0, and then calls the first syscall. So we are at this thing. Move puts again one like 64k syscall, and then it's the last one which initializes the heap with 0. So now it returned from allocator init, and here we should call, so this is the address of the main function. So let's step, so this should be like we breakpoint this thing, right? Okay, so now we are inside of main. So first call, or I guess first like this one is like, let's continue. So here we pushed 0, here we push 41. Let's break, and here we push 4b. So if we jump to this, so let's breakpoint here, and we continue. Here it's the, so this is the actual breakpoint that we cared about. Right, interesting. Yeah, I mean, we don't have, would have been nice if we had the value of heap start, but I missed it. That would have been cool. Anyway, let's step instruction. So now we are inside of show n. Then it's a bunch of function calls. Yeah, maybe actually it's more useful to figure out, oh, see, it's more useful to figure out where, so this thing, if I do the syscall in Rx, I should have the start of the stack, and if we just go here, we allocate the on the stack, and here I should get the address of the heap. So 4130 is the actual address of the heap. Let's continue. to here. So I can just examine, for example, 4, 8, I don't know how to do that though. 8x, right? So that's what's currently on the heap. I cannot really nothing on the heap though. I guess it's the first item. So if I do 24, I should see the first one like 0, then we see the 75 and 65, right? So if I, so here is the test. But why is it a test? It's test if it's like a boolean. So let's jump to this one. So let's breakpoint this and let's continue. So it's a false. You can see that it says it's 0. Interesting, it says it's false. And if I do 32, I should also see the boolean, which is 0. Interesting, so comparing these two numbers actually gave me false. Quite interesting. So if I step instruction, jump is not taken because it's false and it falls through the else. So that means in example SL, it goes to the else case. So wait, did I do the mistake I was talking about earlier with less than? So here we have n and I. If I is less than n, we do the if. And that's right. Probably I made a mistake here somewhere. Right, so it might be worth to try to continue until breakpoint 5 actually. So here, so if we step instruction, I cannot do next oh, I can do next instruction, holy. So let's try to examine more, like 64. So we have 75 and 60. Wait, I can even do decimal so we can just see it like normal humans. Okay, wait, are we lizards? No. Okay, so next instruction, and let's check the memory. That one didn't do anything. Dupe. I mean, obviously didn't do anything because it actually did something on the but how can I show this thing as a single number? Because here it's interesting, right? You see 4130, which is this one, then again 4130 and the 10, so it's this one, and then again another 10, right? So it's this one. But how can I gdb examine a 8-byte word or something? like I don't like to show it like this. I'd like to see it as a single number. Oh, word X maybe. So is it word X? Yeah, so I have to use Q. No, the fuck? I mean, it's a bit better. Yeah, it's a bit better. But let's show only one keyword, right? So one keyword where we can show 8 keywords. So we see on the stack we have, this is the first line. So if I show this one, but I have no idea why it changes the way it prints stuff. Like that's weird. 1D, 2Ds. Like why does that? No idea how, like why it converts it like this after I printed it once with the other one. It's so lame. Anyways, you can see that we have this one twice, right? Yeah, because I don't know why it modifies that shit. Like it's so annoying. Anyway, so right, this points to a 0, then we have another thing that points to 75, and then this thing points twice to 65 basically. That's not really what we expect, right? We want it to point twice to 75 because that's the big number. But what did we put on the stack? God damn it. So we push 75 and then we push 65. So 65 is the first argument and 75 is the second one. Right. So why is it the other way around? The fuck? It's extremely strange, I'll be honest. So we have this one and this one. And yeah, I mean, I guess on this, maybe it's, let's show more stuff from the stack. So let's show 12. So basically on the stack, we pushed 75 and then we pushed 65. Makes sense. So 65 is on top. 65 is on top. Oh, so we push them in the reverse order, yeah. So 65 is on top. If I call dupe, it's gonna duplicate 65. So maybe I should do them in the reverse order. Like that's the way to actually have it. 65 is the first thing on the stack, so it's also the first argument. No, it's not right. Probably I fucked up here somewhere. So let's maybe try to take the 14 function and let's try to recompile. So I need to save this function somehow. Maybe I'll do like temporary or something, and let's let's also delete it from here, and let's store it. Okay, so we are gonna need that function. Okay, anyway, I mean, I guess I can put it into the code itself, so into main. Let's just put it here. So out int, I think it's, yeah, I still have that. Nice. Okay, so we have the out int function. Where does it start? Here. Output integer. I mean, it's output integer as a character for now, but it's fine. It's just outputting a character, right? So I'm really annoyed that this was a bit of a waste, but it's still fine. So here we have out, and we want func out. We don't have it yet, but we'll add it. So let's go here, and let's just say we want function out. Okay, so we don't need to worry about that anymore, but let's try to fix this one. So I'm not going to use show n. Let's use this one. So we have 0 on the stack for the return. Then we push, as I said, if we push 75 and then 65, this is going to be on top of the stack. So wait, do we actually need to do it like this though? What the actual fuck? Because 75 will be on the top of the stack, right? So if I do dupe, I will actually duplicate 75, which is the top of the stack. If I rotate, I push it back. If I swap these two, I duplicate again this guy, then ni. And was I wrong with the explanation for this guy? So I is the top of the stack, it gets popped, so it's the first argument of less than. Man, like it's pretty weird, because here show n will take these two. So like 75 is the n. Maybe I fucked up with the explanations for less than and greater than in that case. So let's see inside of main, let's see how less than works. So we use a less than, right? So less than takes the first item from the stack, it pushes it into, you know, temporary value, then it pops the second item from the stack, and it compares the first thing that we popped. So it's gonna compare I with n, right? And if I is less than n, it's gonna set less. Okay, so that makes sense. So here, I guess no, for less than I was right. It pops these two, or I guess it uses these two, and it compares this one with this one. Yeah, I have to double check all the order of arguments, because Sometimes it's the reverse for some reason. But anyways, so ni, right? If, so it consumes that, it dupes I, right? It dupes the I, it outputs the I, then it does 1 plus, so it adds 1 to the I, it swaps them around, and then it calls recursively to show n. So n is going to be the first item again, and this one here. Like, why didn't this one work? So let's just next build. So result whatever. So it shows a k. Like what? Like clearly there is something weird here. So we have 0, then on top of 0 we have 75. Like 75, I'm pretty sure it's the so chr 75 is k. So maybe it's let's step into this one. So maybe it's so like this one should be the okay, so it's true, right? So the jump should be taken. Nice. So now it calls dupe out. So that was the call to out. I don't think it showed a K. What the fuck? But why? Why did I have N? Like, maybe I made a mistake here. So if I dupe, I get INN. If I rotate, I push the first one to the back. If I swap these two around. If I dupe, I duplicate that. If I rotate, I push this one. Oh, no. I push it here. So it's Nini. Wait a second. Let's run again. Let's go into this function, right? And let's check. Let's check the stack. So 64 from the stack. 64 from the stack, we have 0, first number, second number. All right, we haven't started yet. So if we go here and we check again the stack, we should see that we duped the second number. Can I examine from here? So we duped 75. That's exactly what we did. Then we rotate. So we should see. Wait, no, we do what? Yeah, we rotate. So why does it say? So it was 8, 10, 10, and now it's 10, 10, 8. Wait. Maybe I fucked up with the rotate implementation. Let me just see. Maybe I made something wrong with rotate. So rotate goes from CBA Oh shit, yeah, I did. To BAC. So it actually takes the last item and it brings it forward. So it's the reverse of what I said. CBA, and it brings it forward. So it's actually, after rotate, it's gonna be N, N, I. So I don't need this swap. Interesting, do we want it like this? Yeah, so I was actually not paying attention, I guess, when I did rotate. So function rotate is gonna actually do what? B, C, A, right? It takes the last item and it brings it forward. I mean, I guess it's rotate in counterclockwise, right? Because it's like that. And yeah. We can do two rotate functions, right? One that works like this and one that works the other way. Okay, and then we use another rotate here, actually. So this one, what it's gonna do is, so here we have these values after the dupe. So it's gonna be I, N. And we want to compare N with I. So maybe I could just use this instead. So and N greater than I. Yeah, N greater than I. Yeah, I'll have to think about the order of arguments, because here you can see that the order is matching this. Okay, if we don't use any other rotates, I guess this should work. Oh, I meant the next build. Though I'm not sure. Yeah, so that was actually the problem. The fact that rotate worked differently than how I said it worked. Okay. Yeah, I mean, I guess we could try to use show n, but it's not really gonna work because first characters are not printable, right? So if I do show 100, it's gonna print some characters, actually. So yeah, I mean, we could like, we could just rename it show n, and yeah, it is what it is. And what is actually the character code for enter? Python 3, or the new line is 10. So we could do something like 10 out, right? So it prints some characters. This one is kind of useful. And what's the ord of 0? 48. So like if I do 548 plus out, it should say 5, right? Yeah, I mean, it's 50 because we print the status, but we shouldn't print it anymore, right? Like, we don't care about status code anymore. Right, so we could have out digit. I mean, yeah, whatever. Doesn't really matter. Let's just take this one. So I want to replace it here in here. So show m I to n. Yeah, whatever. We can say that this is an example of a function shows the characters from I to n. Right, so I have this rot function, and we can say the rotate function can be used to rotate. I mean, it's the same. Rotate will take it's gonna take basically the last item and put it in the front. That's what it does. And we can actually have rot prime that is gonna do the thing that this guy said it does. So we could have the both functions, right? Like rot prime does here is gonna be CAB. So we have rotate clockwise and rotate counterclockwise. So is this clockwise or counterclockwise? Let me think. So it's counterclockwise, right? Rotate prime, and rotate is gonna be clockwise because it takes the first one, and if you draw a circle of how A moves, it's moving from here to here, so it's like in this direction, and C moves the other way around. If you go, you know, from the top, I mean, you can be dummy down and say, oh, but it's from the bottom, but you know, go to the top. Okay, anyways, let's leave it like that. So we can have rot prime if that's the case, if we actually need it. I don't know if we need it. Let's just add it because it's gonna be easy. Famous last words. So I'm gonna do that, and now we can say rot prime is the rot prime function, and let's just have, and this is also interesting because we test if our lexer or compiler can differentiate between the same words. So rot p, what it's gonna do here, we are gonna have ABC, and we want to result into CAB, right? CAB. Yeah. We move the first to the end. So we pop C, we pop B, and we pop A. And then we want to push. Wait, yeah. We want to push C, so we push location 0. We want to then push A, so we push, wait, what the fuck? We push location 2, and then we push B, so we push location 1. Right, so now rot prime is gonna do what we think it does. So if we go to example and we use here rot prime and the reverse thing, it should still work. Right, so maybe this is an example of using rot prime, but I don't really care. Yeah, so what's interesting is that I always say that functions take in arguments in the reverse order, but that's not really true because they are not arguments, they're just the stack. So yeah, maybe that's a small mistake then. Like for example, dupe, rotate, and so on take the arguments from the stack, but this one takes the arguments like it would, you know, a normal function. Plus does it as well like that. So maybe I want to fix that. So like greater than compares the first two items in the order that you present them. So here I would really want to use less than, right? Because it's in. So let's go to main and let's see. So we have plus. You can see that we push the first item. I mean, it doesn't really matter. Wait, let's think about it. So plus. So we don't make the mistake again, right? We push the first item. What I would really want to do here instead is move into RDI and then pop RAX. Alright, so now the first item from the stack is the first argument and the second item. No, what the fuck? Yeah, the first item from the stack is the second argument and the second item from the stack is the second argument. So I think that's how I want to do it actually. Just switch these two around. RDI here. RX, like for multiplication and that one, they don't really matter. But for greater than, less than, it will kind of matter. I mean, what I could have done as well was to just switch these around, RX, RDI. But I feel like this one, it's also fine. Yeah, whatever. So yeah, here we do like that, and then again RDI, RX. Right, so now if you go to the README, god damn it, I was wrong with this one. So now people that didn't watch this part won't know that you actually have to use this order, so the normal order that you would expect. Yeah, so it's not really, it's more like this 0, 1 less than is gonna be true. Right. So even for this one, okay, I guess, yeah, whatever. So it's fine after all. Right, at least we can have it like, which is a bit more intuitive, honestly, like it's better. So here we just use less than because we see on the stack I and N. right? And maybe, so a small thing that I changed, I don't think I told you guys, but at some point in the emit data structure, all right, here I switched them like in the reverse order. So I thought that functions take them in the reverse order, but actually what we figured out today is that they don't. So what I'm gonna do for data structures is also give the arguments in the order that they appear. So for example, if you remember, so let's just nix build to make sure that everything still works there. Okay, if you remember, I mean, I guess I can just kill this example. So out. Oh, I don't know what this does, but we'll see. Let's check out what it does. Okay, so I don't really know. I don't remember what this function was doing. So here, yeah, let's take care out of this one first. So it duplicates the item and it prints it. So what I want to do actually is 48 plus. So we can see a one. We can see a one. Sorry, right? Then we duplicate it, and 110 less than, it's gonna end it. So I should do like this. So we are gonna print first first 10. Let's do first 3. So it's gonna be 1 2 3 4. If I want to print only the first 3, I should swap and less than. Wait, what? So, oh, so it's gonna be 1 2 3. Oh, yeah, it's because I print first. But even if it's 3 though, that's weird. Wait, what the fuck? So it's gonna be 3 at some point, right? It's gonna be 3. Okay, so it prints the 3, then 3 swap, less than 3 is less than false. Wait, what the fuck? Yeah, this doesn't really make sense, but because this one should be on the if case actually. Right, it should be on the if case. So it's like we print something and then we take that number, right, which is a 1 first time. So 1 3 less than, we go recursively. Yeah, 1 2 3. I don't know why I put it the other way around. Anyway, interesting. So on the base case it returns 0. Right, so here it will return 0 as well. Okay, anyways, right. All right, so yeah, let's do actually from 1 to 10, and let's do it like this. Let's do something like dupe 6 equals if we do this one, otherwise we don't do anything. And if it's equal to 9, we also print it. What do you think is gonna happen? 69. Yeah. So that's that. But here for IVEC, right? So I said I reverse the order. So now IVEC, this is X, this is Y. Maybe I have to zoom in a bit. This is X, this is Y. We call the constructor. Then complicated actually takes in these guys like that. Complicated. We duplicate it, so we take the N, we swap, we take the IVEC, we call this thing and that. And then if we call out, and then maybe a 0 for the status code, it should say E. And what do you think is the character code for E? Wait, what? Oh, it's ORD. It's 69, you are right. Okay. So this should actually print E69, which is the, we can also say 10 out, and it's gonna be, yeah. So it kind of works now, the out keyword. So let's see if we can actually add the strings. But yeah, I think, you know, that debugging stuff kind of took too much, but still fine. Maybe we can do something like really simple for strings. So quote. Yeah, we need a quote, right? And let's add stack token string. What the fuck? Case stack token string. Let's at least try to do the lexer, so we are a bit more advanced when we try to right, but I mean it's gonna be a bit difficult. I think I also have to remove quotes from names, but I'm not sure yet. Like if I do the else if before his name, it should be fine. So if the character is symbol quote, I don't care about the rest. Right, if we have a quote, then we want to read string. So yeah, let's first, let's say to do actually implement, but first let's create a string slice, right, with position 0, and while our character is not symbol quote, so this is the simplest way to do it, but we have to read a character first. Oh, or I guess we can use a do while, because why not? We can just use a do while, and it's gonna be like read one character and then check this, right? So that's how we get the string. So now let's just do something like token string, we pass the slice position. So this thing doesn't really work that well because we don't check for escaped characters. We have to check for escaped characters, but that's the only other thing we need to add. So here when we read a character, we need to check if ch is equal to backslash. Huh. You cannot... Yo, is this a bug in C? I mean, obviously not, but we need to check if it's backslash. Right, that's what we need to do. And if it's backslash, then we need to read another character and do some extra stuff on top of that. But we'll figure out next time what that thing is. So if I actually go now into... Do I need to do anything else? I don't think so. Let's go into tests and let's add a test for strings. 09 string.sl. And obviously we are gonna have hello world. That's gonna be the easiest test. 10 string.sl, and this one is gonna be escape. Right, so we have some escape codes, and even like this one is not gonna work yet, and you'll see what it's gonna output as well. So let's build, let's test 09 should work fine. I mean, we just test the lexer. Oh, excuse me, what? I guess I forgot something. If we read that thing, I guess we still need to do a read once, right? And obviously we need to check for end of file and all of that good stuff, right? So yeah, that works. Okay, but if we check, then it's like kind of broken, right? So tests 09 string.ref, this one works, but then string escape.ref should be ref. It should be hello world, and I guess with escaped characters in it or something, right? So if we run nix run checker, it's gonna fail on the last one. So I guess that's fine for now. Yeah, we were stuck with the debugging for a bit too long for that rotate function, but we'll try to implement strings next time, right? And maybe even have an out function that works properly somehow. Like maybe have a function that converts integers to strings. Actually, that's gonna be interesting to do. So we'll see if we can do that. So we actually have numbers, and I'll add the more operations like division, modulo, because we'll need those. So yeah. So far, no, I'd say it's pretty decent language right now. So maybe after we add strings, we can try to do something like rule 110, right? Like proving the language is Turing complete, although, yeah, we'll see if it is. I mean, it should. Pretty hard to do a language that's not Turing complete, I would say, but who knows? And yeah, so we'll actually see, in the next part. So let me just show the one that worked, right? So we are able to print the stuff like characters. So yeah, I'd say that's pretty good progress right now. We are finally, like, it's day 8 or 9, something like that, and we are able to print characters. So I'd say that's pretty good progress. I mean, it looks like it's not, but we have if statements, we have functions, custom data structures. So I'd say it's pretty good progress, even though we can only print characters for now. But yeah, we'll do strings next time and try to convert integers to strings. That's gonna be kind of useful. So yeah, thank you for watching and see you in the next one.